You might say, why do we care? Well, chemistry is all about like breaking bonds and making bonds. It's what your body does all day long. So that's why we care, because we're trying to break and make bonds. So we have this thing called valence bond theory. And this is one of those things where you have a theory and then they kind of keep upgrading it as the years go by. But valence bond theory, it describes a covalent bond as something of half-filled atomic orbitals. And the key word here is overlap. I've got a picture to show y'all in a second. Of half-filled atomic orbitals, each containing 2 electrons. Now you already knew that they contain 2 electrons. Like if I point at this bond, how many electrons are there? You would say 2. How many are there here? You would say 2, so you know that. The only thing we're talking about is we're just saying that before we just said draw a line, it represents 2 electrons, and that's the covalent bond. Well, now we're saying, hey, do you guys remember that really there's this 3-dimensional space that electron went into, and it was like a sigma space? Do you guys remember that? That's what we're kind of saying. Well, if you got an electron in one space, so it would be like on the hydrogen right here. So see, there's hydrogen's electron. And then if you have like another electron in like some other 3D space, so like we're just gonna make like here. And I need to do this for a hydrogen-hydrogen bond, so I'm gonna move him off of that atom for a second. So like if this is a hydrogen, what we're saying is instead of just drawing a line between the 2 hydrogens and saying, oh, hey, look, these are a bonding pair, is what we say is like this guy kind of gets close and then this guy kind of gets close. And that is overlap. See, because they are thus overlapped. So not a tricky thing. It just seems weird at first. You're like, overlap, half-filled atomic orbital. Well, when there's 1 electron in it, that's a half-filled atomic orbital. Because you can only have 2 in the bond, and 1 is half-filled, and 2 is your max you can do on any orbital, S, P, D, or F. You can only have 2. All right, so those are your half-filled atomic orbitals, each containing 2 electrons. And they yield a pair of electrons shared. Hey, this is covalent chemistry, so we're shared between the 2 bonded atoms. So when they make this kind of a shape, they kind of then can jump in and out of each other's space. So like that one can go there and they can move all over. Y'all good? Hopefully you're good. So there are 2 kinds of bonds. There is a sigma. I know you thought I was about to say single, didn't you? And a pi. Now I don't know why we changed the names on these per se, but look. So your sigma bonds, that's your single bond. And they both even start with S's. Now your pi bond, it builds more bonds onto your sigma. So like what we're saying is that the pi bonds are double or triples. But it's the double and the triple part of it. I'll show you what I mean. So let's say we're talking about sigmas. I'm going to make sigma's color be red-ish. So here's our sigma color. So like this is sigma, this is sigma, this is sigma, this is sigma, and this one looks like it's between. So I'm going to call that one sigma. So this one has 5 sigma bonds. That didn't look very much like a sigma. And then over here, so 1, 2, 3, 4, 5, 6. That's 6 sigma bonds. So now you're like, but that other thing was a double bond, and you said something about double bonds. Yes, yes, yes. So this guy right here, that is the second part of this bond. You gotta have the thing I've colored kind of reddish pinkish. You've gotta have that in place first. They call it frameworking, or you gotta have that first, and then you can get the double bond. You can't just jump to a double bond. You gotta have that in place. So this one has 1 pi. And then over here, this is 1 and this is 1. So I need to have 2 pi. So when you get structures like this is a really common question. It'll say how many sigma bonds and how many pi bonds. So you count all of the singles just like we did in both those cases, so it's not tricky. And then you go back and you count only the doubled part. Like the additional line as 1 pi bond per section. And like this next line is a pi and this next line is a pi. And of course, we'll show you exactly what they look like, which is kind of crazy looking. Then we have hugely important concepts. Chemistry is all about asking about bond strength and bond length. All right, so bond length. Single bonds are longer. Remember, we got that little sigma. Double bonds are not as long as singles. Remember, this is what we were just saying. Sigma. So that was that color right here. That's your sigma. That's your sigma. That's your sigma. That's your sigma. Your double bonds are about medium, and the triple bonds are really tight, and they're really narrow bonds. Now notice that for strength. So here's your strength. Watch what happens with your little arrows. Do you see how it's reversed? So if we were looking at these molecules, this would be the longer, this would be a long bond, and this would be kind of like a medium length bond taken together. That's medium together, and that's long, like if I'm comparing those two. But then if I was asking about strength, I would say this one is weaker, and this one is stronger. And yes, the more bonds, the even stronger they are. So of both of these molecules, this is going to be your strongest and your shortest bond. So if you can get all those principles I just said, you've got the majority of the chapter nailed down, in all honesty. If you've got those two, you're okay.